High-speed, high-rise elevators. A quick guide. Abstract, this paper highlights the new trends in high-speed elevators and discusses the impact in modern buildings design, construction, and operation. Additionally, it focuses on the technological innovations and how these are implemented in high-speed elevators. All these implementations are resulting into a modern, comfortable, safe and energy-efficient vertical transportation. As these implementations are penetrating, the overall calculations are affected, and new parameters are inserted to an integrated application. Keywords: energy efficiency, roping, safety components, European norms. Introduction. The modern trend in city built, that includes tall buildings, would not be feasible without the development of faster and more reliable elevators. Nowadays the largest metropolitan centers have competed each other in building such buildings which are considered as landmarks that reflect dynamism and financial growth. At the same time, another competition takes place, the one that has to do with the fastest elevator. It seems that Olympic Games motto Citius, Altius, Fortius is a constant pursuit of every human activity. At the present paper we are dealing with the modern trends at high speed, high-rise elevators, and we are presenting the features that differentiate them from conventional ones, as well as the calculations in such elevators according to the European norm 81-50:2014, 81-50, 2014. Chapter 1. Tall buildings, high-speed elevators. According to the Skyscraper Center Institute, the tall buildings are discriminated in three categories based on their height: H. Talls H300m, Super Talls H300m, Megatalls H600m. Nowadays, there are 3 Megatalls and 151 Super Talls buildings worldwide. The following chart shows the 10 tallest to-tip buildings worldwide, with descending classification as they are referred to the cbta.org. The tallest to-tip building is Burj Khalifa, Dubai. Its height reaches 828 meters while the highest floor is on 585 meters. Far East and Middle East countries have plenty of tall buildings while USA follows that pace and Europe lags. Nowadays, the fastest elevator has a speed of 20 mph. This elevator is installed by Hitachi in 2016, in the Skyscraper CTF Financial Center, number 7, 530 m high, located in Guangzhou, China. It needs 43 seconds to travel from the lowest to the highest, 95th, floor. The previous record was held by Taipei 101, number 10, elevator, in Taiwan, which is traveling with 16 m/s, 60,6 km/h, speed, whereas inside the tallest building, Burj Khalifa, the fastest elevator travels at speed of 10 m/s. Elevators at a speed higher than 1 m/s require technologically enhanced parts to meet the demands of a normal operation. The tests of such improved parts must take place in real conditions. Therefore, the large elevator companies invest in elevator test towers constructions. 2.2 Machine Room-less elevators, MRL. In such elevators, the motoring machine is placed at the headroom of the well. Therefore, there are no space requirements for machine room. To overcome the problem of space narrowness inside the well, gearless motoring machines are developed. The roping ratio is usually 2:1. The first MRL elevator developed in 1996 by Kone, Finland. This model named Kone Monospace 2,3. MRL elevators are applied to low and middle rise. At high-rise elevators it is preferred to create a separate machine room space, however it is use gearless motoring machines. 2.3 New types of elevators. New advanced elevators have been developed for more efficient passenger service in tall buildings. These new advanced types are double-deck elevators, where two separate cars are connected, and they are traveling inside the same well. In this way, the capacity of the elevator is doubled. These cars are not integral, but they can be divided to run independent travels inside the well. Anti-seismic elevators, which are detecting the early imperceptible earthquake vibrations that occur within 7 to 30 seconds before the main vibration, P waves. This function leads the passengers to leave the car safely at the closest floor. Then and if the S waves do not exceed a predefined limit, the elevator is set to operational mode. Green elevators, with high energy efficiency. This type of elevator saves significant amount of energy consumption, has low carbon footprint, and returns energy to the indoors energy requirements of the building. Jump elevators, which are useful during the construction phase of a building. That is because the machine room of the elevator can slide to the guide rails and rise the same time with the rise of the building construction. Ultra-high-speed elevators are shaped aerodynamically to reduce the air resistance, the noise, and the vibrations. Also, aerodynamic shape of the car is useful for the effective setting of the atmospheric pressure inside them to avoid the pain in the passengers' ears. Smart traffic innovations are applied to modern elevators to achieve shorter standby and travel time. These are: destination selection system, where the passengers are obliged to choose their destination floor before their boarding to the car. Then, an advanced software informs them to go to the more appropriate car for their destination. This innovation causes significant time saving to passengers' service. Express elevators, which are leading only to specific floors that are defined as sky lobbies. Then, the passengers are transferred to other elevators to reach their destination. Currently are testing elevators without ropes. At these modern types of elevators, the traction would be magnetic. Moreover, the rotary motors will be replaced by 4 linear motors with permanent magnets, placed to the 4 corners of the elevator cars. This technology is already applied to ultra-high-speed trains. Chapter 3. Parts that are differentiated in high-speed elevators. 3.1 Motoring machine. A major technological innovation of our times is considered the gearless motoring machine, which is used at high-speed elevators. At these, the traction sheave is connected in line to the motor, removing the need of reduction gear use. As a result, there are no energy losses, no noise caused by reduction gear, power savings, less volume, and weight. 3.1.1 Permanent magnet synchronous motors, Pmsm. Gearless machines are using exclusively Pmsm, which can rotate with low speed equal to the traction sheave's speed. These are multipolar motors with 3-phase current field coils at the stator only, while in rotor there are permanent magnets instead. They are considered as a great technological innovation, and their development is an aftermath of the discovery of new strong neodymium magnets. 3.1.2 VVVF inverters. Pmsms are driven exclusively by VVVF inverters, variable voltage variable frequency, which are setting accurately the motor's rotation speed and torque by modifying properly the frequency and the voltage of the power supply for. Therefore, VVVF inverters achieve smooth motor operation both in acceleration and deceleration. Furthermore, VVVF inverters recycle energy, because in generating mode the generated power is destined for inside building power needs. The use of VVVF inverters provides to the motors the following advantages. 3.2.1 Ropes construction type. Seal, S, 1-9-9, they have 3 layers consisted by different cross-section wires at each layer. However, every wire in a single layer has the same cross-section with the other wires that are included in the same layer. The outer layer has thicker wires which are more resistant to abrasion but not to bending fatigue. This rope type is used when it is necessary to last longer rather than not get abrased, example for elevators without many pulleys. The outer layer wires are alternately thick and thin. This feature gives the rope higher flexibility and resistance to bending stress, however it deprives resistance to abrasion compared to seal ropes. These ropes, W, are used when it is necessary to resist to fatigue bending rather than to outer layer abrasion, example for elevators with many small diameter pulleys or inverse bending pulleys. Filler, F, 1-6-6-12, they combine the advantages of S and W ropes. They include thin wires for higher flexibility, larger fill factor for higher resistance to fracture, and thick wires in the outer layer for better traction with traction sheave. Such wires are used at high-speed elevators, where little elongation, large fill factor, higher flexibility, braking, and flexural strength are required. 3.2.2 Elevator ropes for tall buildings. Mid and / or high-rise elevators must deal with the following problems. Ropes elastic elongation. During passengers' entrance in the elevator, takes place an undesirable drop of the lift car because of the rope's elastic elongation. Rope's plastic elongation. Permanent elongation. Plastic elongation occurs due to the constant tensile that the ropes are submitted. That's because of the weight of lift car and counterweight. Even at the early operation of an elevator, the ropes are elongated plastically. And after a period, the elongation is so intense and as a result the counterweight drops on the buffer. At this point, it is required to cut part of the ropes. This task is expensive and requires immobilization of the lift car. 3.2.3 Rope Untwist. During the elevator's installation in a tall building, it is possible for the ropes to get untwisted due to their own weight. The untwisted ropes have less resistance to abrasion and their life cycle is significantly decreased. The untwist should be clear and distinguishable. Therefore, the ropes in tall buildings have a colored line drawn along the rope. The manufacturers of ropes constitute that the untwist should not exceed the 1/2 of a full round every 10 m of a rope. Lang-type ropes are more liable to such untwist because the individual wires are wrapped around the center of the rope in one direction. Ropes with the proper specifications and requirements are used in tall buildings. Steel wire core ropes are preferred in this case due to their higher breaking strength and less plastic elongation. 3.3 Compensation chains. The force resulting from the mass of the ropes acts variably, because it acts either on the part which suspends the lift car or on the part which suspends the counterweight. We do not often concern about the compensation of this variable force in conventional elevators, because it is considered negligible. However, in high-rise elevators, 30 m, the mass of the ropes is so significant we cannot ignore it. Thus, it is necessary to compensate it. Compensation chains are used for this purpose. They are installed to connect the down area of the lift car with the down area of the counterweight. For this connection are used riveted tensioning pulleys at the bottom of the well. According to N 81 to 25.5.6, for nominal speeds that exceed 3 m/s, it is obligatory to compensate the weight of the suspension rope 7. For lower speeds, such means are optional. For lifts whose rated speed exceeds 3,5 m/s there shall be an anti-rebound device as well. Compensation chains are covered with a flexible plastic PVC material, to insulate the noise of their movement. The choice of the appropriate compensation chain is based on the weight per meter, which is desirable to be identical with the total suspension rope's weight per meter. At 2:1 roping, the weight of the compensation chain should be twice as much the one used for the 1:1 roping. 3.4 Slide guides. During the lift car travel across the slide guides, sometimes it is observed undesirable vibrations, sudden unexpected movement, and noise due to guides misalignment. At high elevators, these imperfections impact drastically, while in conventional elevators they rarely lead in irreversible situations. Furthermore, the tall buildings are susceptible to climate conditions. In high winds, some high-rise buildings could sway as much as 45 centimeters off-center, for a total sway of 1 meter. Extreme temperature variations cause expansion and contraction of the building, as well as earthquakes can make the deviate from the vertical line 8. Thus, the more the structural elements of a building are suffering, the more serious impact that have to lift's installation misalignment. That is the reason why in high-rise and high-speed elevators are applied roller guides. An elevator car navigates between a pair of rails that are attached to the structure of the building. He wheels of a guide surround the rail on 3 sides, helping to control side-to-side and front-to-back movement. These rollers include 3 or 6 roller tires which are laminated by neoprene rubber. This design has been special engineered to dampen noise and vibration. Moreover, they are spring-loaded to compensate for unbalanced cars or misaligned conditions. 3.5 Mechanical safety components. 3.5.1 Safety gear, overspeed governor, OSG. At high-speed elevators it is required the use of progressive safety gears, both for lift car and counterweight, according to the accepted rule of N 81 to 27. Progressive safety gear for lift car when U 0,63 m/s. Progressive safety gear for counterweight when U 1 m/s. Safety gear for counterweight can be replaced by a safety gear for lift car that triggers also in the ascending direction. A safety device for rope braking. A safety device for sheave or sheaves axis braking. According to N 81 to 27, for progressive safety gear the average retardation in the case of free fall of the lift car with rated load or the counterweight or the balancing weight shall lie between 0,2 g and 1 g, 5.6.2.1.3. So, in case that the nominal speed of the lift car is u equals 3 m/s and the deceleration provided by the safety gear is equals 0,6 g equals 6 meters per square second, then the overspeed governor, OSG, should be fly ball type and should be activated when the speed of the lift car exceeds the limit of 1.15 on. When OSG triggers in the up direction, then the tension weight should be bigger compared to the weight that is used for down direction. The bigger the tension weight, the less the rope slipping during the OSG trigger. OSG ropes are fatigued in greater tension, thus, they need to have greater braking strength. 3.5.2 Buffers. At high-speed elevators are used energy dissipation buffers. These are hydraulic buffers consisted of one piston rod, one metallic spring and a cylinder, divided in 2 tubes, inner and outer cylinder, which are communicating through small, drilled holes in the wall of the tube. When the piston rod is pressed, the hydraulic fluid is forced out through the hole and is collected to the outer cylinder. After the buffer has impacted and the piston rod is released, the compress spring returns the piston rod back to the starting position. High-speed elevators require deeper well than usual, for buffers use 9. Moreover, for ultra-high-speed elevators are used 3-stage telescopic buffers. Chapter 4. Calculations of lift components according to N81-50. 4.1 Guide rail calculation. Guide rails should be dimensioned according to the worst-case scenario, i.e., lift car loaded with its full payload. When compensation chain is used, then its weight should be considered in the overall calculations. However, payload is not static, so it is more accurate to consider that it acts off-center of the lift car. That is the reason why N81-50 defines two different applications of the payload's position in the lift car: 10. 1. Payload Q lays 18. Off-center. 2. Payload Q lays 18. Off-center. For each one of the two applications there are three conditions that should be examined. 1. Safety gear activation. It is considered that safety gear is triggered, so the overall load applied to the guide rails is multiplied by K1 factor. 2. Regular operation. It is considered that lift car is traveling with steady speed. The overall load applied to the guide rails is multiplied by K2 equals 1,2. 3. Car lift load. It is considered that car lift is stopped at a floor level, empty, while the 40% of payload is applied at the car lift entrance. These conditions are examined to evaluate if the resulting tensions are lower than the maximum permissible tension of the guide rails material, equals 205, 2/1, bending stress, y-axis. 2. Bending stress, x-axis. 3. Compression stress. And tension stress. 4. Combined bending and compression/tension stress and evaluation if it is equals. 5. Flange bending stress and evaluation if it is equals. 6. Guide rails. And buckling stress. Maximum permissible deflection equals 5 mm. 4.2 Calculation of minimum permissible safety factor on suspension ropes. N81-50 refers to the minimum permissible safety factors on suspension ropes, considering the specificities that any installation might have: 10. The total number of traction sheaves, NT, and the total number of pulleys, NP. Traction sheaves and pulleys diameter, DT, DP. The number of pulleys with simple, DPS, or reserved bends, DPR. The value of the groove angle. The rope's diameter, D. 6. Final calculation of safety factor SF, in accordance with Ni-Quivi and ratio derived from Fig 10, PAR 5.12.3, N81-50. From the previous process, we reach to the following conclusions. A traction sheave equals to bigger number of equivalent pulleys compared to a regular pulley. That is because the overall tension in suspension rope is greater in traction sheaves because it is a result of bending stress and wear due to slipping. A reversed bended pulley has 4 times larger number of equivalent pulleys from a simple bended pulley. The DT/DP is affected heavily as the pulley's diameter gets decreased. That is because in the calculation process this ratio is raised in the fourth exponent. The minimum SF gets increased as Ni-Quivi gets increased and as ratio DT/D gets decreased. 4.3 Traction calculation. 4.3.1 Tension calculation at both parts of suspension rope when car lift is accelerating or decelerating. The suspension rope's traction occurs if the condition 1-2 equals is true. Where T1 equals rope stress at the car lift part, 0.2 equals rope stress at the counterweight part, E equals 2,71, natural logarithms base, A equals angle of wrap of the ropes on the traction sheave, F equals friction factor, for sheaves with V groove, F equals 2, equals friction factor between suspension ropes and traction sheave, equals groove angle. The value of slipping limit, Fi, is only affected by angle of wrap of the ropes and the friction factor F. The traction or the slipping of the ropes depends in the tension ratio 1-2 of the two parts of the ropes. It is observed that when the car lift is moving with acceleration or deceleration, the stress that is acted by the masses of car lift and counterweight, they are simulate artificial gravity, G plus or minus A, rather than real G. 4.3.2 Evaluation of traction in traction sheave. When a lift is planned to be installed, the traction examination is fundamental. The traction condition is 1-2 equals. Is the friction between the ropes and the sheave? Is the groove angle? Traction should be tested at the following conditions through the evaluation of 1-2/ratio. First condition, lift car in the well with 125% of the rated load. Second condition, emergency braking condition. Traction should be ensured in two sub-conditions. Lift car descending at the lowest point of the well, loaded with 100% of the rated load and decelerating due to emergency brake. Third condition, counterweight stalled condition. These three traction conditions are represented in the following table for both direct and indirect roping. In every table we examine additionally the use of compensation chain, which is necessary for high-speed, high-rise elevators. It is worthy to be noted that the use of compensation chain improves the traction in every condition and in both types of roping. The dynamic and kinematic features of traction or slipping are differentiated in elevators with indirect roping because the moving speed of the suspension ropes is double to the moving speed of the car lift. The deceleration of the suspension ropes is double to the deceleration of the car lift, in case of emergency braking. The masses of car lift and counterweight are acting by half at the rope part stress. It is observed that when safety gear is activated when car lift is moving up, the required tension weight is times bigger to the required tension weight when car lift is moving down. It is also observed that for given tension weight, the activation force of the safety gear in the up direction must be Fa times smaller than the activation force of the safety gear in down direction.